our goal for today is to talk about the second derivative. And so we have a good understanding now of the first derivative because it gives us information about how the function behaves as far as increasing and decreasing. And of course, you might ask yourself the question, well, we've had one derivative, yes, but what about second derivative? Great question. So that's what we're going to get into today. Now, before we begin, make sure you have a good understanding of what the first derivative tells us, because we're going to build off of that. After all, the second derivative is the derivative of a derivative. And so, well, let's begin. Now, if we think about what's happening with derivatives, the derivative tells us whether something is increasing or decreasing. So the first derivative tells us when our function is increasing, decreasing. In other words, if I know the sign, if the first derivative is positive, well, that means that as I go from left to right, I'm going up. And if the first derivative is negative, as I go from left to right, I'm going down. Now the second derivative, well, that tells us when the first derivative is increasing or decreasing. So now we have some sort of notion of what's happening to our slopes. So what does that mean? Well, if our second derivative is positive, that really means that our first derivative is increasing. And we call this concave up. And what that means is that as we move from left to right, so we always have this orientation of left to right. Calculus, orientation is very important for calculus. So what that means is we look at our slope. So if you look at the slope over here, for instance, it's a negative slope, and then it gets less negative, it gets eventually to 0, and then it starts going more positive. So if you look at our slopes, they're going from a negative to a 0 to a positive. That means our slopes are increasing. Now, what happens if our second derivative is negative? Well, that says our first derivative is decreasing, which means we're concave down. And so our curve has this kind of a shape to it. And again, you can just think about taking some tangent lines. So initially you have a positive slope, then it's less positive, gets to a 0 slope, and then it gets more negative. So again, just think of the slope, just follow it. Positive, less positive, 0, negative, more negative, so forth and so on. So as we move, again, left to right, that we see our slopes are going down. Now, what's another way to think about this? You know, the name's concave up, concave down. In some sense, you're like, well, concave up, it's like a bowl that's facing up, and concave down, it's a bowl that's been turned down. That's not so bad. It's a reasonable way to think about it. But it's also telling us information about what's happening to our function. So one of the things is we know that the first derivative we can use to get the tangent line. And the tangent line is telling us something about the local behavior. Now, the thing to remember is that if I have a tangent line, so let's say this is our tangent line here, that our function doesn't fall on the tangent line usually because most of our functions aren't flat, but it's close to the tangent line. So you might ask the question, all right, where is the function going to be? In other words, how am I going to move off of the tangent line? So here's sort of a nice little idea. And it goes like this. If you're concave up, so that says your slopes are increasing, your function will sit above the tangent line or on the upside. So the concave up says that my function is coming up from the tangent line. Okay, so that's what we can think of as concave up. Now, of course, keep in mind, all of this is very local. And because that's what information about derivatives tells us. It says, here's what's happening nearby. And nearby can be very nearby. But, okay, so locally, though, I'm coming up from the tangent line. On the other hand, it's the case that if my second derivative is negative, then what that translates into is I'm going to come to the bottom side or down below the tangent line. So my function would be behaving more along the lines of the following. So concave up, my function really moves above the tangent line. Concave down, I'm moving below the tangent line. They might want to say, okay, wait a second, that's if my second derivative is positive or negative. what if our second derivative is 0? Well, that's a great question. Well, the thing is we don't have enough information. And in some sense, the second derivative is 0 is an important point because that's when we can switch the sign of the second derivative, which means we can switch the concavity behavior. So we have a name for that. So we call that an inflection point. So an inflection point is a place where if I look on the graph, the concavity is changing. So I'm going from something that's concave up to concave down, or vice versa. So an example, very simple example of that, of what an inflection point does, is if you look at the graph y equals x cubed. Well, it's not so hard to take a derivative, that's 3x squared, and it's not so hard to take the second derivative. It would be 6x. And what you can see is that the second derivative is 0 at x equals 0. So it's negative when x is negative and positive when x is positive. And you can see that, lo and behold, we have the right shapes. Because notice that below 0, our curve fits into sort of this piece here. It's concave down. While when we are above 0, it fits more along to that piece there. So this is concave up. And so we have a transition from being concave down to concave up. Now it happened to be that the derivative was 0 at 0. It doesn't have to be 0 to have that change in concavity. So essentially, what should we think of as an inflection point? An inflection point happens at critical points of the second derivative, but not every critical point of the second derivative is an inflection point. So you always have to test what's happening to the concavity on either side. And what can we say? Okay, so that's the second derivative. It's telling us information about how the function is coming off of our tangent line, is one way to think about it. Or if you like, how the slopes are changing. So how do we use the second derivative? Well, one thing we can do is something called the second derivative test. And you might recall we have something called the first derivative test. Well, this is the second derivative test. And in the first derivative test, the goal was, well, we have critical points, but what kind of critical points? Are they mins? Are they maxes? Are they neither? And so now we're going to say, all right, that's using information from the first derivative. Now, what if I want to use information from the second derivative? So really the second derivative test, again, this is a case where the name gives it away, is all about using information from the second derivative. So you need a couple of things to happen. You have to have a critical point, and it has to be the case that you can talk about the second derivative at that critical point. So it's not just any kind of critical point. It's a critical point where the first derivative is 0. So we're not going to use the second derivative test on boundary points. We're not going to use it on points where the derivative is undefined. Only where the first derivative is 0, and then we have a second derivative. And the test is actually simple. You only have to check one thing. Now, if you remember the first derivative test, we had to check both sides. And we had to say, well, what happens here on the left-hand side? What happens here on the right-hand side? And understand the behavior. The second derivative test says, no, just at the point. What's happening at that point? And then we can figure it out. So here's the test. So plug the point where the first derivative equals 0 into the second derivative. If it's negative, it's a local max. If it's positive, it's a local min. And if it's 0, it indicates that more work is required. Usually the first derivative test is the more work. Now, if you need help in remembering what's going on, there's this very cute, silly little mnemonic device here, which says, all right, here's how it works. So I'm going to think of the possibilities. So the second derivative is positive. So see, the two pluses. The 2 because it's the second. Then the curve is a concave up curve, so it looks something like this. And if the second derivative is negative, so then they put 2 minuses, then the curve is a concave down curve, so it looks something like that. And if the second derivative is 0, so here you have 2 zeros, then you don't know. There's just not enough information to decide. So that's what's going on here. And so, lo and behold, we say, oh, if our second derivative is positive, for instance, we're a local min. Well, that's because that's what the shape is doing. And if the second derivative is negative, we're at local max. Well, again, you see, second derivative, local max, it's peaking out. Now, how can we verify this or show this? Well, there's a couple of things. We can go back to what we just talked about of things being concave up or concave down. We know the first derivative at our point is 0, which means that our tangent line looks like this. It's a flat tangent line. And now we have our point here, C. So if we're concave up, that means that we are going to be above that point. So concave up would be up here. So this is the second derivative positive or concave up. And then, of course, we have the other possibility, meaning that we're concave down. So if we're concave down, that means that we're going down, our function comes down from the tangent line. So our second derivative is negative, we're concave down. And there we go. There's sort of our intuition. Now we can be a little bit more precise, if you like, or at least make it feel like we're doing more. Let's think about what's happening. Here's another way to see what's going on. Suppose for a second we know that our second derivative were positive. All right, so what can we say? We know we have our point C, and we know that f prime of C is what? Well, it's 0. That's our assumption. Our assumption is f prime of C equals 0. All right, now, our second derivative is positive means that our derivative is increasing as we move from left to right. So our derivative, if I move from left to right, it has to increase. So if I'm 0 and I move to the right, what has to be true? Well, what has to be true is to the right, my derivative has to be a positive value. I have to increase. What if I'm to the left? Well, in order to increase to 0, that says to the left, the derivative had to be a negative value. All right, so that says, hey, I actually have to be coming down, and then I had to be going up. So I can see I have that down-up situation, and therefore second derivative being positive means I'm at a local min. Similar argument shows what happens when the second derivative is negative. Now, there's of course a question. We have two tests. Do we need them both? And which one should we use? Generally speaking, the first derivative test is a little bit more powerful because it applies, for instance, at endpoints are where the first derivative is undefined. So it can be used in more cases. Now, at this point, you're probably saying, great, so I don't need to know the second derivative test. And the answer is, no, hold on. There are good things about the second derivative test. So what are some nice things about the second derivative test? Well, one thing that's nice about the second derivative test is that it's, well, okay, this is a spoiler alert. All right, shh, don't tell people I'm telling you this. But when you get to multivariable calculus, there is no first derivative test in multivariable calculus. But there is a second derivative test. So in other words, it's more general. It works in multivariable settings. But that's something for Calc 2. Is there another reason why we might want to care about this in Calc 1? Well, in order to use the first derivative test, what do you have to know? You have to know where your critical points are at. So in order for me to apply the first derivative test, I might say, hey, this is, my critical point is here, and I'm trying to understand what's the behavior. Is this going to correspond to a local min, local max? Neither? Well, in order to apply the first derivative test, what I have to say is I have to plug in a point on the left, and I have to plug in a point on the right. And so far, you're like, I'm with you, so what's the challenge? The challenge is, how do you find the point to plug in? You have to make sure that whatever your point you pick is close enough to this critical point that there is no other critical point in between. So if you're not careful, you might say, oh, I'll pick a point here. I'll pick this point right there. But lo and behold, it might actually be the case, oh, whoops, there was actually a critical point there that you missed. and so you're not catching that right behavior. Now you might say, well, yeah, but it's easy to know where my critical points are. Well, for the examples we've been doing, but it's pretty easy to come up with crazy examples, not even that crazy looking, where it's not easy to spot where the critical point is. So what's the moral here? Well, for the first derivative test, if you're not sure where your critical points are, it can be not clear if you're close enough testing what the behavior is. So that's why you have to be careful with the first derivative test. In the second derivative test, you don't have to worry, am I close enough? Because you're only looking at that single point. So there are definitely advantages to using the second derivative test. So that means know them both, which is great. It means we get to learn twice as much. All right, good. So now what have we done? Well, we've learned about the first derivative, which tells us something about increasing, decreasing, and we've learned about the second derivative, which tells us something about concavity, which means we're ready to talk about another topic. And this one is called curve sketching. In other words, I want to see what the picture of my curve looks like. Now, nowadays we take it for granted, how do we plot the picture? Well, we ask a computer. So how does a computer plot a picture? So the basic idea for a computer is it does something along the lines of the following. It says, well, you asked me to draw a picture. What I'll do is I'll draw many, many little dots and do it many times. And then, and it might need to or might not, depending upon how many dots, I'll just connect the dots. And of course, there's so many dots that you can't even tell that this is what the computer did. And especially with nowadays modern computers, the screen resolution is so sharp, you can't tell. But that's what they're doing. Lots of dots, and they connect the dots. Now, not so bad. It's a pretty straightforward approach. But there is, of course, a downside, which is lots of computation is involved. But computers like to compute. It's in their name. So for them, it's a wonderful thing to do. But suppose you have to do it. Okay, well, so there's the computer. Here's us. All right, what are we going to do? Well, the last thing we want to do is spend a lot of time doing computations, because that's actually can be very time-consuming and tedious, and especially when we don't really see a lot of variation. So what we're going to do is something slightly different. So a computer, I guess we should summarize, what does a computer do? They're doing a lots of connected dots. That's how we should think of the computer. Now what we're going to do, this is us, we're clever. We're going to do high-powered connected dot. Now you're probably thinking, that sounds very similar, Steve. What's the difference? All right. Good question. What is the difference? Well, what we're going to do is, instead of plotting every single individual point, we're going to say, let's find the important points. So what are important points? Well, important points are places where we have critical points, and in addition, we're going to throw in inflection points. So those are the places where we see behavior changing in the curves. So for instance, for us, we'd say, well, we might say there's a critical point here. We can even say it's a maximum. There's an inflection point, say over here. There's another critical point there, which we can say is a minimum. And so now we have these pieces of information. And what do we want to do? Well, we want to connect them in a smart way. So, all right, I'm getting ahead of myself. But the goal here is that we only want to plot like 3 pieces of information and then connect them with a really good approximation for what the curve will look like. It won't be perfect, but it's going to capture the quality of the curve, which is the really important thing. Okay, so how do we do it? So we find all the points where the first and second derivative are 0 and undefined. So essentially the critical points and inflection points, and we mark them. So here we are. We've marked our points. Now, what comes next is sort of a fun little thing that says, let's understand the behavior between points. So if I've marked a point here and I marked a point there, the question is, how is the curve behaving between those 2 points? And for that, we want to get into what's the sign of the first and second derivative. So how do we do that? Well, so there's 4 possibilities. We have the first derivative is positive, first derivative is negative, second derivative is positive, and second derivative is negative. So those are the possibilities. Now, we're going to put it all together and say, well, what do the shapes look like? So in other words, what does it mean to say I have the first derivative is positive and the second derivative is positive? Well, that means that your curve is doing something like this. Concave up, and I'm increasing. If the first derivative is positive, but I'm concave down, I'm going to be doing something like that. If the first derivative is negative, but I'm concave up, I'll be doing something like this. If the first derivative is negative and I'm concave down, well, then I'm going to be doing something like that. So those are the possible shapes. And so what we can do is we can say, okay, between each one of these points, we can say, what's our behavior? So for instance, here, we might say, aha, we are going to be the case where f prime is positive, f double prime is negative. Here, we're going to have f prime is negative, f double prime is still negative. Here, f prime is negative, but f double prime is positive. And for this one, we would have f prime is positive and f double prime is positive, for instance. All right, so we've marked our points, and now we say, okay, I understand the behavior for how the curve will act in each piece. Finally, I say, all right, now I say, let me apply the appropriate shape to the various places. Well, okay, for example, first derivative is positive, second derivative is negative. Well, that says I should be looking like this. So it's like, okay, and because this is a critical point, I know that I can throw in the where I have flat tangent lines. So I say, okay, so I'm going to be doing that. And then I say, okay, negative, negative, well, that would be this kind of shape. And so I'm going to be doing something like that. And then what's next? Negative, positive, well, that would be here. So I'm going to switch, and I'm going to come in flat. And then I say what? Well, the last one is positive, positive, which is over there. So I'm going to go something like that. So what do you notice? The pictures are very similar because we're capturing the behavior. We're identifying the key points and identifying the behavior between those points and putting it all together and getting a good picture. Now, we can, of course, do a couple of other things that can make us look good. We can find places where it crosses the axes. So, for example, where do I hit the y-axis? We can look for asymptotes. Where does our function blow up? Or what happens as we get very large? And we can look for symmetry. But the moral of the story is, if I want to get a sketch of the curve, I can do that by sort of highlighting the important points, the really good dots, if you will, and figuring out how to connect them in a really good way. And so, in some sense, nowadays we take all this for granted, but it really took a lot of the tools of calculus to make it so that it was much easier to figure out how to sketch some of these curves, because it's not always easy to say, hey, where is the highest point? Not clear on just a random function. So it's a nice way, and it really gets us into the understanding what's the behavior of the function. And it's good for us to understand how functions are behaving. And of course, for that, we should do some practice. So, well, let's go do some practice now. All right. See you soon.